So let's talk about the anthrax attack. This is the post 9/11 anthrax attack. 1 week after the 9/11 attacks, letters containing enough anthrax spores to kill millions were mailed to several news agencies. And this resulted in the U.S.'s first ever death from a bioterrorist attack. Robert Stevens, he was working in the National Enquirer building. He was a photo editor for The Sun, which is a journal very similar to National Enquirer. He contracted anthrax and he died. Then, not too long after that, on October 9th, same year, anthrax letters were mailed. Anthrax spores were in an envelope that contained letters to Senators Daschle and Leahy. And in that attack, 22 persons got sick, and I think it's actually 4 people died from that. The total was, I think the total was 5. Stevens and then 4 others, but I had to check my facts. So the consequences were 22 people sickened, 5 died, and the Postal Service was shut down so they could figure out how to deal with this threat. And of course, many hoax letters followed this. Some of these folks that sent hoax letters were caught, and some weren't. Okay, so those are sort of the bare bones facts. That's sort of what you pick up in a news article, the newspapers. So where's the physics in this? I mean, this is not a biology class. I am certainly not a biologist, but there is some physics involved in this, namely in the dispersal of spores and why they fail to kill as many as one might otherwise think. So here's some of the facts, the more detailed facts about this attack. So a lethal dose, so LD50 dose, it is 2,500 to 55,000 spores according to the DIA. Leahy's letter contained an estimated 2 grams of spores. In case you're not familiar with metric, that's about the weight of a US pen. Okay, so that's how much spores in terms of how much they weigh. And it turns out that that's about 200 billion spores. So written out in numbers there it is, 200 million spores. Oops. Those unprintable characters again. So that's, you take 200 billion spores and divide by, let's say, 10,000 spores per lethal dose. You know, it's be something between 2,500 and 55,000. So I'll just say, okay, let's suppose it's 10,000 is a lethal dose. Something in between there, right? So if I divide those two numbers, I end up with something like 20 million people have a 50% chance of dying. So I just divide that by 2 and say, okay, 10 million deaths. Okay, so there are enough spores there to cause 10 million people to die. And yet, only, and once again, only is in quotes because even one person dying is way too many, but only 5 people die. And 5 is obviously a much smaller number than 10 million. So the question is, why so few? We're glad it's so few, but why so few? So let's do the math a little more carefully. So it turns out a human breathes about 1 cubic yard of air in an hour. Okay? Furthermore, we do know that spores kind of only stay in the air for about 5 minutes before they more or less just fall to the ground. So unless you take your lunch and drag it on the ground and then eat it, you're probably not going to ingest any spores after 5 minutes after they've been released. So it's that first 5 minutes, plus or minus, that matters. So let's just consider 1 cubic yard of air per hour. The lethal dose we're saying is about 10,000 spores. We said that there were about 200 billion spores total that were released. So I want you to pay attention to how I did the math, because we're going to use this sort of approach to solve lots and lots of problems for making estimates. Okay? So what I'm going to say is, well, look, the worst possible case is that each cubic yard of air is going to have the lethal dose of spores in it. That's the worst possible situation, right? I mean, if all your spores are right here and everyone else is in the room not exposed to the spores, then nobody gets contaminated and nobody dies. The worst possible case is when you disperse the spores such that you have a lethal dose in every cubic yard of air that has a person breathing in. Okay? This is the worst possible case. So, I'm going to do some multiplications here. Now, how did I know how to arrange what I'm multiplying by what and what I'm dividing by what? Okay? This is a very, very useful skill to have. All I do is I just arrange things so that my units come out the way I want them. As long as I'm using the right numbers, the numbers that I'm given there, I just arrange things like what's on top, what's on bottom, etc., so that things cancel. For example, I want to end up with how many cubic yards we're talking about. Okay, if I take a lethal dose in each cubic yard of air and I got 200 billion spores, I want to know how many, if I really did distribute it in the maximally destructive way, how many cubic yards are we talking about? And since I want my final answer to be in cubic yards, I start off on the very upper left with cubic yards. That way, that's going to be my final unit down at the end. You see? Cubic yards there, I'm going to end up with cubic yards. Everything else I arrange so that the units I don't want will cancel out and go away. So for example, I have 1 cubic yard per 10,000 spores. That's my maximally destructive concentration of spores. I'm going to multiply by 200 billion. Why do I multiply and not divide? Because if I multiply, the spores in the numerator cancel out the spores in the denominator. Spores are gone, I end up with just cubic yards. Okay? This is a really, really useful way of figuring out when I need to divide, when I need to multiply. Let your units do the work for you. So I'm a real big proponent of putting units into everything because they really help you. This is called dimensional analysis. And especially if you don't care about factors of 2, which we have uncertainties greater than factor of 2 here, but if we're talking about, 10 million people or 20 million people, either way it's a horrific problem. But it lets us get sort of what we call an order of magnitude estimate. If we don't care about factors of 2, we can almost never go wrong just by using dimensional analysis. We don't have to know any formulas. We just make sure our dimensions work out. Okay, so this is a really, really useful approach to making estimates. We'll do this when we talk about energy, when we talk about radiation, when we talk about a lot of things. Okay, are there any questions about how I did this calculation? I mean, it looks kind of trivial in a way, but it's really a prototypical calculation that we're going to do throughout the semester. So anyway, the result is 20 million cubic yards would be the maximally destructive way to disperse this anthrax. How big is that? I mean, it's really important to look at numbers and have a feeling for what we're talking about here. 20 million cubic yards. How much is that? I mean, is it bigger than this room? Probably. But how to get a feeling for this? Okay, well, one way of doing it would be maybe to convert it into something that you're more used to, like maybe, okay, so how many cubic miles is this? A mile by how high that would be. Or maybe you can say, well, how big is the Empire State Building? What's the volume of the Empire State Building? And divide it into this thing. It'll tell you that's how many Empire State Buildings full of air we're talking about, spore-laden air. What the author did, and so that's what I did, he was a New Yorker, so he compared this to, say, the volume of the New York City subway system. Okay, so he just gave a number, and I'm going to sort of estimate that number. So if we consider the New York City subway system, I just went online, and it says that the entire length of all the tunnels in the New York City subway system is 656 miles. They didn't say how big the tunnels were, though. Well, they didn't say how big the cars were. They say they're about 10 feet wide by 12 feet high. And I'm saying, well, okay, let's take a minimal sized tunnel. I guess you're going to have about 2 feet clearance at least 2 feet clearance above the car, and maybe 3 feet clearance side to side, and then I just converted that to yards. So 12 feet would be 4 yards, and 15 feet would be 5 yards. Okay? So volume is length times width times height. The length is the total length of all the tunnels. The width then is 4 yards, and the height is 5 yards. So I just multiply length times width times height. 656 miles times 4 yards times 5 yards. But that gives me some goofy units. It gives me some number times mile, yard, yard. What's a mile, yard, yard? I don't know what that is. I want like yard, yard, yard. It's going to be a cubic yard, or mile, mile, mile. So it'll be a cubic mile, something like this. Since we've been talking cubic yards, I convert it into cubic yards. How do I do the conversion? Once again, I just arrange, so I can look it up, if I don't know, that 1,760 yards is 1 mile. Okay? Now, do I multiply that by that number, or do I divide by that number? Well, 1,760 yards is the same as a mile. So if I put one over the other, it's like multiplying by 1. I haven't changed the amount, I've just changed the number involved. Okay? But do I put the 1760 on top or 1760 on the bottom? I let my units decide for me. I want to get rid of miles and replace it by yards. So I put this number here so that miles is in the denominator. It'll cancel the miles up on the numerator over there, and I'm left with yard, 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 which is a cubic yard, a yard cube. Okay? And so when I multiply all that out, I end up with 23 million cubic yards. Well, look at there. As it turns out, our estimate of maximally destructive concentration of spores is about 20 million cubic yards. So it's not so different. So in other words, that's about as much as all the air in the New York City subway system. How many people can you put in the New York City subway system? Well, at maximum crowd, they say that the peak load is about 5 persons per cubic yard. And of course, not the entire subway system is going to be filled with 5 people per cubic yard. So, but still, I mean, even if it's only a fifth of that average, that would bring me, down to 23 million cubic yards. You must be about 20 million deaths. So, we just did a ballpark estimate. If we go at maximum capacity of the maximum that it often achieves of the New York City subway system, and if we uniformly distributed the spores, but with maximum killing potential, we could have something like 20 million deaths. But we only had 5. Now, of course, you had less people in the building than you have in the New York City subway system. That's part of the problem. But there are a lot more than 5 people in that building. So what's the answer? The answer is poor dispersal. It's not easy to efficiently disperse the spores, fortunately. Okay? I mean, here's this clump of spores, and it's not easy to just take them and somehow uniformly distribute them over the entire building. Probably the best, how can I say, the most destructive thing that a bad guy could do is find a way of releasing the spores into the air handling system for the building. But the bad guy wasn't in the building. The bad guy mailed this stuff to the building. He or she could not control how these spores were dispersed. Even if the person who opened the envelope opened up like this and went to blow it to open it up and spewed out this pile of spores, they probably would have been confined to that immediate area. Okay? So this is the good news for us, is that spores are not typically easy to distribute. And if you don't distribute them uniformly with maximum killing potential, in the case of anthrax, 10,000 spores per cubic yard, you're not going to have the horrific results that the bad guys would want. So this is all good news. But what if they used a different disease? What if instead of anthrax, they had used smallpox? Okay, now you don't worry as much about the initial distribution of the spores or the virus or whatever, you're counting on the fact that it's highly contagious. So if you release enough of it to get a certain number of people ill, then you count on, one person come in contact with 3 more, and then those 3 more get sick, and they each come into contact with 5 more, et cetera, and it's almost like a chain reaction. This is one of the things that's so scary about the Ebola virus. It's not a terrorist-caused catastrophe, but you can see how that could work if it were a terrorist-controlled catastrophe. One person who's sick, if you have a easily communicable disease, acts as a vector for the distribution of that sickness. So what if the bad guys had used something really nasty? Well, anthrax, as I said, is not very contagious. It spreads by the spores, and these spores don't stay airborne that long, but what if it were smallpox? Well, that is a real danger. The good news, in a sense, is that it's ultimately going to be more devastating to developing countries. And usually these terrorists are from developing countries. So ultimately what would happen is if you release these horrible things, let's say in the US, we have a pretty decent healthcare system, and so a lot of people would die, unfortunately, but ultimately the bad guys' own country and own people could be infected and ultimately cause huge devastation in the home country of the bad guys. So, we hope that terrorists would recognize that and therefore not use these highly contagious diseases because of it ultimately coming back and affecting the very people that the bad guy wants to help, you could say. On the other hand, what you could always worry about is religious fanaticism. Okay, so if somebody is a religious fanatic of whatever religion, pick your religion, if this person is a fanatic in that religion, he or she might say, well, our God or gods will protect us from this, and only the people who don't believe in my God or gods will die. Well, then you remove some of the rationality that might prevent a terrorist from taking this attack form. So the author contends, and I am inclined to buy into it to some extent, that possibly the next really nasty terrorist attack with consequences could very well be bio. My money is still on the cyber, but the bio, I think, is a really, really unfortunately good possibility.